Yeah, I would say the programming assignments aren't bad. And actually the reports aren't bad either. The class average in reports is probably lower, but it's probably mid 80s.
Okay.
There's more people that get full credit on programs than get full credit on reports. But there's more people who get very poor grades on programs than get poor grades on reports.
Gotcha.
So it's kind of
It equals out. It's
something. It's somewhere in there. I mean, at the end of the semester, I rolled dice for everybody's grade, anyways.
Huh?
What's up?
Do the dice have
Repeat
A's
that for what?
on all sides?
Which class is this? Hello World?
35.
This guy?
Yes. I can't believe you forgot that many times.
Well, no, I remember that. I just had to remember which of these. See, you would feel sorry for me if you had to teach as many different programming classes per week as I did. Some of them the same language, some of them different language, some of them talking about the same subject, but 2 months from now or 3 weeks ago. Half the time, I don't know what a class has learned and what they haven't.
Well, okay. That's not.
So you should feel sorry for me.
Yeah, I feel sorry because you haven't kept track.
Oh, I try. That's why I rely on the students to tell me what we did last time. All right, so our assignment this time is for today. Well, what was the paper?
The paper was the Euclidean.
Euclidean algorithm, right?
Yeah, that one.
Okay, it was time to talk about time complexity.
Yes.
Okay, so what did we determine from that? The idea of, so the question was what kinds of problems is time complexity? Remind me of the whole topic of the paper. So it was Euclidean.
That whole topic was just a big blur because it was very wordy. But for me to break it down, it was more so like, would you use a long, simple way to solve a problem versus a complex, short way to solve a problem? And your example was the Euclidean formula.
Gotcha. So kind of making an argument as to when is it better to make a clearer, more easily understandable solution to a problem versus a potentially shorter but harder to understand solution to a problem versus certain problems that are time complexity problems that rely on having possibly a difficult to understand solution in order for it to run in some sort of reasonable amount of time. So the example, like your homework assignment dealt with adding fractions together, right? Now, remind me on your homework assignment, you were to store a fraction inside of an array like we have here. So a 2-bucket array, the numerator was in bucket 0, the denominator is in bucket 1. And were you supposed to just be able to add 2 fractions?
Yeah, that's all we add. Just add.
What else were you supposed to do? Add and reduce?
Simplify.
Okay, add and simplify, but just 2 fractions.
Yeah,
So you were supposed to write a method called add fractions that takes 2 fractions in as parameters, where a fraction is a 2-bucket array, and return the result as a reduced fraction. That's the dealio.
Yes.
Okay. So.
Right. It was just add. Don't worry about simplifying.
So we're gonna call this guy static int array add fractions. This guy's gonna take an int array f1 and an int array f2. Okay, so we have 2 fractions, and let's go here and solve the problem on paper first. So let's say that we have the fraction 1/2 plus 1/4. How do you add 2 fractions together? The first thing you need to do is you need to get a common denominator, right?
Yeah.
So the quick and dirty way of getting a common denominator is to cross multiply, right? So the common denominator here is 8. 4 times 2, so the 2 denominators multiplied together gives us 8. So that means we have 4/8 plus 2/8 equals 6/8. So let's try to get that answer first. Then we'll worry about reducing it. Okay? So inside here we need to first get common denominator. I'm not gonna common denom. There we go. So the common denominator is going to be the denominator of each of our fractions multiplied together, correct? So I'm going to say the common denominator is F1 at bucket 1 times F2 at bucket 1. That will give me my common denominator, right? Okay. Then, new numerator is equal to common denom times F, actually, hold on, I'm lying here. New numerator is F1 at bucket 0 times F2 at bucket 1 plus F2 at bucket 0 times F1 at bucket 1. That's our new, right? All right. Then we're going to create our new fraction, integer array. The answer is equal to a new integer array with 2 buckets. We'll say the answer at bucket 0 is equal to new numerator. The answer at bucket 1 is equal to new, common denominator. Common denom, and then return the answer. Make sense? All right. Now let's give ourselves a quick little method for printing out fractions, just so we can, conveniently test this. So we'll say static void print fraction. This guy takes an int array f as a parameter, and it'll print out system.out.println empty string concatenated with f at bucket 0, concatenated with a slash, concatenated with f at bucket 1. Make sense? It actually would have worked. I didn't need to start with the empty string. I just like doing that. So this is taking this integer, concatenating it with the string that is a slash, concatenating it with the denominator. Okay. I also want to then give myself the convenience, a convenient way of creating fractions. So I'm going to say static int array build fraction int num int denom. This guy, we're going to build an integer array named AR is equal to a new integer array 2. AR at bucket 0 is equal to num. AR at bucket 1 is equal to denom. Return AR. So, quick little method to build a fraction really quickly, rather than having to do this all the time. Okay, so what we're going to do here is we're going to say int array f1 is equal to hello dot build fraction, and what was our example fraction? 1/2 was our first one, and then 1/4. Int array f2 is equal to hello dot build fraction 1/4. So everybody, does everybody understand that if I pass in numerator and denominator to this function, it'll take them in here, build me a 2-bucket array, and return that array? So it's just a convenience. Okay. So I'll build my 2 fractions. Then I'll say int array f3 is equal to hello dot add fraction f1 f2. And then we'll say hello dot print fraction f3. And if this all worked to plan, we should get a 6/8. Okay, so there's our 6/8. That make sense? Okay, so now we need to do some reducing. So we'll build another method. Again, harping on what we talked about last time. Notice we're building a lot of little helper methods to do things. Just like going to Home Depot and getting a new tool. So we're going to build a method, static int array. Actually, we don't even need an int array. We'll say static void reduce, and this will take in an int array f as a parameter, and it reduces that guy. So in order to reduce a fraction, let's go back here. To reduce 6/8, what do I need to do? I need to find the greatest common denominator. That is the largest value that evenly divides both the numerator and the denominator, right? Okay. Theoretically, this isn't optimally, but theoretically, the biggest number that could possibly be is the smaller of the two numerator and denominators. So it's the smaller of 6 and 8. Correct?
Yes.
So first thing I need to do is I need to figure out which of those numbers is smaller, the 6 or the 8. So we'll ask a quick question. We'll say if, well here, we're creating an integer called, not answer yet. The let's call it largest possible. Good enough. And actually, we'll start largest possible off at f at bucket 0. We'll assume it's the numerator. Then we'll ask the question, if f at bucket 1 is actually less than f at bucket 0, if that's a true statement, then we'll say largest possible is equal to f at bucket 1. Make sense? Okay. So, right here, we assume that the largest possible common divisor is going to be our numerator. Then we check to see, oh, wait a minute, is it actually the denominator? So after those couple lines of code, largest possible holds the largest value that might evenly divide the numerator and denominator. That makes sense? So now what we need to do is we need to count down to 1. Because we know 1 will evenly divide both of them, correct? Because if 1 evenly divides both of them, then the fraction is already reduced. So we need to count down from largest possible all the way down to 1, potentially, finding the biggest value that evenly divides both. So we'll say for int I is equal to largest possible. Keep going as long as I is greater than or equal to 1. I minus minus each time. Then we want to ask the question, does the current value we're looking at, does it evenly divide both? So we're going to say if f at bucket 0 mod I, if that guy's equal to 0, and f at bucket 1 mod I is equal to 0. Let me space this a little bit. It'll look cleaner, I think. If both of those are true, that is the numerator and the denominator are both evenly divisible by I, then what do we want to do? We want to set f at bucket 0 equal to f at bucket 0 divided by I, f at bucket 1 equal to f at bucket 1 divided by I. That makes sense? And then we actually want our method to end. We're done. We've reduced, correct? How do we make a method end? You do a return statement. So this is a quick way out. This guy returns void, so we don't actually return anything. We just say return. That'll end the method immediately. Alternatively, we can fake our way out of the for loop. We can say I is actually going to be equal to 0. something like that. That'll break the loop the next time through, right? Is 0 greater than or equal to 1? Nope, so we'll fall out of the loop. So that's another way we can break out. And then the method will just immediately will end when it hits the last curly brace. So a couple different ways you can get out of here. We can short circuit our for loop by just changing I right there. We can say return. We also have a command called break. Okay. What break does is it breaks us out of the most local loop. So if we hit a break statement, it takes us right here. Okay, so break would take us out of the loop immediately following a loop. Return makes the method immediately end. That's what a return statement does. In this case, it doesn't return anything, so it's not going to actually return a value. That's why we don't have anything after this guy, because it's a void. But this would make it immediately end. But from what we already knew how to do, probably the easiest solution here would just be set I to something that will prevent the loop from going through again. Make sense? Okay, well, I'll set it to break. Then we'll just hit the end of this guy. So before we return our answer from add fractions, we want to pass that guy to reduce. Now notice that reduce doesn't actually return a value. It's a void. So what am I doing? I'm building my answer. I'm going to pass my answer to reduce, and then I'm just going to return the answer. Will the answer be reduced or not?
Yeah.
Why? Because we changed the memory address. When we passed reduce the answer, we passed it a pointer to this fraction. And we actually changed the real fraction there, the guy up in space. So that in the end, when we return the answer, we return a modified version of the answer. So there's our 3/4. Make sense? Okay. So that is a... does that solve everything from the homework?
Yeah. Okay. I have a question.
Mm-hmm.
I use something called recursive loop. Okay. For the GCP. And I send you an email and you said yes, that's what I'm talking about.
Mm-hmm.
And
Well, you did it with the you wrote the Euclidean algorithm. You wrote a greatest common divisor.
yes.
Yep.
Okay.
Yeah, we'll write that.
Okay. And I use something called LCM, like least common multiple.
Right, but you wrote that, right? You wrote a method called LCM. Yeah. That's fine. Yeah, the real part of your question when you asked me via email, can you use recursion?
Yeah.
I mean, point is that you know how to call a method. Nothing keeps you from calling a method from within itself.
Because it's kind of like a part of that report. You know, it's a time complexity is a different. We use it like loop and recursive.
Yeah, which is actually ironic, because recursion is usually, we'll talk about recursion, but recursion is usually inefficient. Yet in this particular case, recursion isn't what makes it efficient, it's the algorithm that makes it efficient. Yeah. All right, so now let's see this break. So any questions about this so far? You can kind of tell this is, this kind of works. This solves the homework at the simple case. All right, well, let's go. And let's start building up a bunch of fractions. So we've done random numbers in here already, right? We've never generated a random number?
I watched it on your other lecture, but we didn't.
Okay, well, let me show you how to, let's generate some random numbers. So I'm going to create an object of type random. Are you sure we didn't do random numbers in here?
No.
No random number.
Yeah, but you can't program. I'm not going to believe you.
Okay.
I'm
I'm not gonna Undisputed on that.
All right, so I went ahead and created a variable named R of type random. Notice it's underlining it because it doesn't think I've imported something, so I need to import java.util, which is where the random guy lives. Random has a bunch of methods in it. One of those methods is the next int method. So just to give you an idea here, let me do a little loop. We'll print out 10 random numbers. Okay, so inside main, I created an instance of the random class, which is a tool for generating random numbers, pseudo-random numbers. Then I'm going to spin through a loop 10 times and just print out 10 random numbers so we can kind of see what kinds of things get generated by that. Okay, so those are 10 random numbers. Now, just by looking at these, what could you tell us about the output of r.nextInt, of the nextInt method? Actually, let me ask you another question first. What is r.nextInt? What is that guy? What is nextInt?
Another like integer.
It's kind of like a loop into
Well,
the range of ancient.
Just by looking at it, forget that you even just saw it work. What is that guy?
Another integer.
Return.
So it's an instance method. How do you know it's an instance method?
Ah,
Okay, well, how do you know it's a method to begin with?
Because the table
We
without
didn't
that
have
class
to-
name.
We didn't have to.
parameter.
Parameter list. It's a method because of the parentheses, and you know it's an instance method because of the way it's being called. We're calling it with R, with it, which is an instance of the random class. So this guy, nextInt, is an instance method which lives in the random class. Make sense? Now, what he returns is a pseudo-random integer in the range of all integers. What does that mean? What's the smallest integer that you could possibly have? Negative 2 billion and some odd. What's the biggest int you can have? Positive 2 billion and some odd. So this is going to return us a random number between negative 2 billion and positive 2 billion. That make sense? Okay, now I want to make sure we have a random number between 1 and 500.
So then you put one parenthesis.
I didn't teach you that method. This is the method you have right here. You got a method that will give you a number between negative 2 billion and positive 2 billion. Now I want to get a method. I want to write a method here.
Feels something like more.
All of y'all sick. I need to stay away from.
No, I've been doing pretty well. That's why I'm a little concerned about them.
I don't know. You hacking up your organs, he hacking up his,
the
and then
American
Ali
version.
hacking up his.
Well, I have an excuse though. I
What?
had McDonald's tonight, so I have gluten.
All right. Your allergy is excusable
Okay, I might just keel over here.
this time.
Plus, I see Portillo's. It's more gluten. What'd I get? Hot dogs? Yeah.
Next time, bring enough for the whole class.
Well, not for the whole class. Why would he do something foolish like that?
Because he's bringing you stuff.
I'm important.
We are too.
Not to him. He's great. Oh my gosh, there's like a bunch of crap in here. Man, feel the weight on that. I love that.
It looks heavy.
I know, it's so good. What was that rating?
A get random number.
Oh, get random. And we're going to have this guy take in a low and a high. All right? And what we want to do is we want to return a random number between low and high, including low and high. That make sense? Okay, so that's what this guy does. He returns a random number between low and high, including low and high. So if I pass it a 1 and a 10, it would return a number between 1 and 10, including 1 and 10. Okay? So, I'm going to go ahead and create my instance of random in there. Then I'm going to generate a number. So now, after that line, num is some number between negative 2 billion and positive 2 billion. And I need to somehow get it to be a number between low and high. How would I do that?
I'll call the method and put in.
For loop, using for loop, we can do sign.
Okay, so we'll do it the bad way first. Okay, so what he wants to do, you actually probably want to do a do while loop, because you need to do it at least once. So we're going to say do I'll define it outside the loop. So generate a random number, and then keep doing it. Like, do it again if the random number you generated is less than low and greater than high. It's an or. So if the number I generated is either too little or it's too big, generate it again. Otherwise, we hit the lottery and we return num. That make sense?
Do we need equal sign to include the high?
I said less than. So if it's equal to it, it'll pass it through. We're good. So now instead of printing out this, we're going to print out hello dot get random, and we want to do what, 1 to 10? 1 to 500?
Yeah.
Okay. And we're going to print out 10 of these. Well, that wasn't too bad. We ran pretty quick. One to 10 should be a lot worse.
1 to 2.
Well, it's still trucking. We're stuck on working on our 5th number now.
Why is it taking so long?
Because I'm literally generating a random number over and over and over again until I finally get one. I'm generating a number between negative 2 billion and positive 2 billion.
Oh, gotcha.
Over and over and over again until I finally get one between 1 and 10.
That's a lot.
That make sense?
Yeah. Can you scroll down any code?
Nope.
Come on. Thank you.
Okay, so this will accomplish what we're trying to accomplish. Doesn't necessarily do it well, but it does accomplish it. So how can we do this better?
I mean, you can like take the high minus low, take the result and mod that generate. That's 5, 3.
Okay, so let's say that we're doing a number between 1 and 10. And I generate a number between negative 2 billion and positive 2 billion. Well, the first thing I need to do is I need to make sure the number I generated is not negative, right? So how do I do that? So I'm going to generate a random number.
Multiply -1.
Always multiply it by -1.
I mean, if you want to check the result, yeah, check.
Well,
I need to
yeah.
check it first.
Yeah.
I don't want to multiply a positive number by -1.
Right. So you'll get it.
Okay, so if num is less than 0, then we'll say num is equal to num times -1. So after this if statement, we're guaranteed to have a positive number. So now num is some number between 0 and 2 billion, right? It used to be between negative 2 billion and positive 2 billion. Now it's guaranteed between 0 and 2 billion because I just made it a positive number. Okay? But now I need to get it to a number between high and low.
Yeah. High minus low, the result is from more original number.
Well, let's go this route. Let's just say low is 1. Let's say high is 10. How do I take a number between 0 and 2 billion and guarantee that it's a number between 1 and 10?
Need two if statements. If it's less than 10, number is less than 10.
Generate, do another random number?
Yeah.
Yeah, I think we want to avoid the whole creating random numbers over and over again thing. He wants to use something with mod.
10 minus 1, that would be like,
Well, just use
Okay.
use 1 to 10 as the example. So I have some number between 0 and 2 billion, and I want to somehow get that number down to a number between 1 and 10.
What with the high?
Okay, so we're gonna take 10. So we're gonna take, let's say the number is 1,000,000. 1,000,000 mod 10 gives me a number. What a number in what range?
10.
0 to 9.
0.
0 to 9. So any positive number mod another positive number n gives you a range of results 0 to n minus 1. Right? So if I mod something by 10, I get 0 through 9. If I mod something by 40, I get 0 to 39. That make sense? And then add 1. That make sense? So if high and low, so actually for right now, let's just do it with 1 through something. So we are going to return num mod high plus 1. So num mod high will give us some number between 0 and high minus 1. We add 1 to that, we'll get some number between 1 and high. That make sense? So I changed the nature of my method just a little bit, so now it just takes in a high number. We'll just assume it's always 1. So this should give me a bunch of numbers between 1 and 10. 10 of those numbers. Significantly quicker? What if I go to 500? Still quick? Okay. So, what we want to do is we want to add a bunch of fractions together, keeping a running total. So, let's start with just 10 fractions. So we're going to create a starting point fraction. So we're going to say int running total is equal to hello dot build fraction, and let's just start with a 1/2. That'll be our starting. This is int array running total. That'll be our starting fraction. We'll start with a 1/2. Sound good? Now we want to start adding fractions together. So we're going to say running total is equal to hello dot add fractions. First fraction we're going to add is running total. The second fraction we're going to add is a brand new fraction created with hello dot build fraction, whose numerator is hello dot get random 500, and whose denominator is build fraction to 500 as well. Actually, I'm sorry. Numerator is that. Denominator is one of these guys. Okay, so that'll be my denominator. And I can kick this down a line, I think, and so we're calling add fractions. The first fraction is running total. The second fraction is the fraction we're building out of a numerator that's some random number between 1 and 500, and a denominator that's some random number between 1 and 500. That make sense? Okay. And let's do that 10 times. So we're going to just keep building up on our running total. And then ultimately we're going to say hello dot print fraction running total. I got a negative number there. How How did that happen? Well, why don't we come in here and why don't we see what our fractions look like? So when we came into add fractions, why don't we do a little print statement? System.out.println adding fractions. Hello.print fraction f1. Hello.print f2. And we'll see what those fractions look like. So we're adding fractions 1/2 plus 137 over 92. Then we're adding fraction 183 over 92, which was our reduced original one, and 326 over 215. Then we're adding fraction 69,337 over 19,780.
Yes, that's just 52.
Then we're adding these fractions. Then we're adding these fractions. Then we're adding these fractions.
And come back again 52 from minus, yes. Because the range of integers minus 52,000 to
Range of integers only goes up to 2 billion.
Yeah.
My numerator's got too big. I went around the block. Have we talked about that already? Okay. Does that make sense? So I actually need to be able to handle even bigger numbers. Arbitrary size integers. Right? Well, how do I handle arbitrary size integers? Say this again? Okay, well I can use double. That won't be arbitrary. That'll just be a little bit bigger. I can use longs too. That would make it bigger, right? I need these guys to work for any size integers. Well, what's a number? What if we had to build math? So let's look at writing an object. Actually, I want to do that. For right now, just for the sake of argument, I'm going to make all of these longs. Instead of its.
you can create another memory if you like to get string.
Yeah, but then you actually have to do the math with it. I think we are going to do it. This will be long. Add fraction will take in 2 long arrays and return a long array. Print fraction takes in a long array. We can get rid of our print array here just to clean this up a little bit. These are stuff from last class. Okay. So let's see if we have all positive numbers now. It's not done yet, by the way.
Yeah, because those look like they still can be reduced, and some of the numerators are still like it.
It's still cooking. We'll print out final answer at the very end, so we'll know when we actually get to the very end.
What did you say about our final before? And catch that out.
I'll probably just give a final homework assignment.
Oh,
Like an extra one or just like a final? Like the ones that
I don't know. Maybe like a final homework assignment?
okay. like
isn't like homework number 7 the final one?
homework and the paper, or just the programming? You talking?
Well, probably at least 2 papers.
Stop. What's the project that's open?
It's not done yet. My code's still running.
You didn't answer a question.
What was the question?
What's the project that's out there in the grade book?
What project?
I don't know, in the grade book there's a project.
Oh, you already told me the grade book doesn't work.
Okay, well I'm just asking. I know, but I just was wondering.
Oh, nothing that I know about.
Okay,
That's hilarious.
till next week when he's like, oh, here's a project.
Seriously. All right, my program's still running.
Is he even giving you a new answer yet?
No, just in the process of reducing.
Oh.
This guy right here. See, when we added these 2 fractions, we had to multiply this guy by this guy to get us our new denominator.
Yeah, and that's coming.
Then we added the 2 numerators together, and now we're trying to reduce this monster fraction. Problematic, right?
Yes.
Okay, so now let's just go ahead and stop this. This literally could take like an hour or 2 to finish running, potentially. I mean, it's a roll of the dice, but what we've just witnessed is a time complexity problem.
Right.
Okay, adding fractions seems like it would be a very trivial task, and it really isn't difficult to implement. But we just saw that unless you reduce fractions in the correct way, it actually can be quite slow. Well, let's go back and revisit our reduce method. Right now, our reduce method figures out what is the largest possible value it could be. Correct? And then goes through everything between 1 and that. Do we actually need to go all the way up to that?
Mm-mm.
We can actually go smaller, correct? How much smaller?
That minus it.
Minus
Well,
of mod.
if it's 1 less than the numerator.
2 with the
Or
large.
am I? Oh wait, am I thinking
F0
about
is
this right?
1, and you can go F0, the second one F0 minus F1, and go. Like if you have 9 and 3, you can go with 9, 6, 3.
Look and see if it mod itself, and if there's a remainder after that, then divide.
Oh, okay. I see. You want to keep cutting it down by more than just 1.
Yes, because then that way it
Okay. And so how much do you want to cut it down by?
Like if you have like F0 and F1, you can start with the biggest one and minus with the like smaller one. I mean, if you have like 9 and 3, you can start with 9, 6, 3.
Well, if your current fraction is 3/9, and you're looking to reduce that, you're going to go to look at the numerator and denominator. You're going to pick 3 as the biggest possible number, right?
you'll get,
Okay. Then you're going to start doing some division.
you'll
No,
get 1/3.
some mod. No. I thought you were talking about the LCM. No, about the GCD. Go with the mod.
Well, I'm talking about reducing in
Reducing.
general. The whole problem of reducing. Whole problem of reducing. I don't need to check all the numbers between largest possible and 1. I know for a fact that largest possible will evenly divide largest possible. Will evenly divide whichever, either the numerator or the denominator, correct?
Right.
Do I know that it will not evenly divide the other one?
Well, if
can.
you don't have, if you mod it and get a 0, then it evenly divides.
That's how we check it. But a second ago you said, after I find something that doesn't evenly divide both of them,
Right. Then
maybe I can do something other than just subtract 1.
Right.
What can I subtract?
That was
Wait,
one.
you can. I would divide it by itself, and then whatever that number is, just kind of. Oh wait, I lost my train of thought. Never mind.
You can go with the largest one minus the small one.
Couldn't I say I is equal to I minus largest possible? This is the update each time. So the very first time through, I know that largest possible will evenly divide one of the either the numerator or the denominator, because largest possible is equal to either the numerator or the denominator, right?
Right.
But if it doesn't evenly divide the other one, then I know I need to try again. I am wasting my time trying anything inside that range because I know that the next value that will evenly divide either my numerator or denominator must be whatever it currently is minus largest possible.
Oh, so then.
So let's say largest possible was 10. Or let's say largest possible was 100. Okay? And my current value is, well, I need to give you a bigger number than that.
Hold on, wait. So if the I is equal to largest possible.
Well, he was saying it goes down to 0.
Right.
I'm trying to get you on I'm trying to take you on the have step, the halvesy step before we do the full. Well, I might as well show you the full thing.
Make it like easier. So largest possible minus 1.
Well, no, we'd still do largest possible because you want to start at. The example would be this. It'll just be easier if I write it this way. I guess we can do it on a small scale. So if I'm looking at these two, this is the numerator, this is the denominator. My largest possible variable would be equal to 6.
Right.
Okay? So the question is it possible that 6 divides 6?
Mm-hmm.
Yeah. Is it possible that 6 divides 8?
Yeah. Well,
In
no.
this case, it doesn't. So I would drop down to a 5 the next time through, right? Does 5 evenly divide 6?
No.
Can 5 evenly divide 6?
No.
Didn't I know that ahead of time?
Yeah.
When I had a 6 here, as soon as I knew that 6 didn't evenly divide this guy, I need to find some number that evenly divides both of these.
Okay, we need to subtract 6 each time.
Okay? But then the problem with that is, if I subtract 6 from that, I'm down to a 0.
8 minus.
So the 6 is
So you,
the lowest.
But it's not.
2 is the
2 is.
So you to subtract 6 minus 8 minus 6.
What we're looking for is what is the quickest way to get a 2?
Start going to it, starting with 1.
I had you guys look at the Euclidean algorithm, which is a way of doing this quickly. What I want to do is I want to stumble upon that. So rather than just copying an algorithm that already exists, I want us to figure out how do we get a 2 quickly, given these as our possible numerator and denominator.
Let's start with the 6 minus 8, we get 2. Start 6 minus 2, get like 4. 4 minus 2.
Okay, well,
Until we get that
let's
number.
give ourselves another fraction. So let's give ourselves 13 18ths. Okay, that guy's already reduced, right? Okay, and let's give ourselves 12 14ths. Not reduced. All right. So, by our current algorithm, what we're doing right now, if we did for this first one, we're starting with the 6. We're saying, does 6 divide 6? Yes. Does 6 divide 8? No. Does 5 divide 6? No. Does 5 divide 8? No. Does 4 divide 6? No. Does 4 divide 8? No. Does 3 divide 6? Yes. Does 3 divide 8? No. Does 2 divide 6? Yes. Does 2 divide 8?
Yes.
Answer. So we had to do a lot of checking there, right? Next one. 13. Does 13 divide 13? Yes. Does 13 divide 18? No. Does 12 divide 13? Does 12 divide 18?
No.
11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Does 1 divide 13?
Yes.
Yes. Does 1 divide 18? Yes. Already reduced. 13, we take 13 divided by 1, and we take 18 divided by 1. That's our new fraction. Okay? 12.
12 goes into 12 1, 2.
What's the final answer of this one? 2? 2. So it's going to be 6 sevenths. Okay? So, how can we come up with the 2, the 1, and the 2 more quickly?
You can do the family and
We take the largest number and then subtract 1 each time. But we've been saying,
Take the largest number and subtract 1 each time?
well, largest possible, like your variable largest possible, and subtract 1 each time.
Well, that's what we're doing right now.
Right, but
I want to do it better than that.
can we decompose the numbers?
Okay. What do you mean?
Like 12 equals 2, natural is 2 and 3. 14 is 2 by 7. Then decompose.
or you can just
Yeah, like most of the
If
numbers,
you do the math.
default is 1. What do you want the other numbers?
That's the Euclidean.
Right.
Yeah, we want to come up with the Euclidean without finding the Euclidean. What were you saying?
Yeah, like all the numbers divide by 1, so it will straight away make it back to 1. From the real number to 1.
What about
I'm going to throw one more fraction in here. That'll be our confusing one. 8 sixteenths.
It goes into 16 twice.
So our current algorithm is extremely efficient for reducing that guy, right?
Yeah.
That's 1/2. How do we know? Well, largest possible is 8. Does 8 go into 8? Yep. Does 8 go into 16? Yep. 1/2. Done.
So divide.
So our current algorithm worked fine for this guy. Perfectly optimal. But for all these other ones, especially this guy, for a fraction that's already reduced, took forever. Imagine that this guy was a really, really, really large prime number. What's a prime number?
Number that can't be
A prime number is a number that's only evenly divisible by 1 and itself. Right? 3 would be an example, 5 would be an example, 13 would be an example. Imagine a gigantic number that is prime.
That's a check first.
Huh?
Check first. If it's a binary number or not.
If it's a prime number?
Yeah.
Ah, interesting you should say that.
Yeah.
That's another time complexity problem.
Yeah.
If you have a gigantic number, detecting if that number is prime,
You gotta go through all the
you
numbers
can
in
like-
between.
What I know in
Zero
math, if you
and
have like divide by 2, 3 like 15, 1 plus 3 is 4. And if the first number 3 2, it will divide by 2. If not, 13 is 1.
that's not going to
No.
cut it.
No, because
Large prime numbers. I mean, here, let's go down this path. So let's say we want to write a method called isPrime that takes a long as a parameter. And this guy should return true if long is a prime number and false otherwise. Well, how do we do that?
Yeah, if number is equal to 2, then it's false.
'Cause 2 is a special case.
Yeah, 2 is a
Okay? Just for the sake of argument right now, let's forget about 2. A prime number is a number that's only evenly divisible by 1 and itself, correct? So I need to check all the numbers between 2 and the number minus 1. And if any of them evenly divided, return false. So for int I is equal to 2, I is less than L minus 1, I plus plus. If L mod I is equal to 0, return false. Else, return true. We need the else. So if I am still alive after running through that minefield, after checking all the numbers between 2 and L minus 1, if none of them evenly divided L, L must be prime. So return true. That make sense?
What about if we don't multiply 2 and 3 and 5? All of them is non, that's fine.
Yeah, those are all prime. So we're coming up here. Let me just comment all this out for a second. Okay, and what I'm going to say here is I'm going to say num is equal to, I need a random object. R dot, actually, no, I don't need a random object. We have a method that gives it to us, right? Hello dot get random number, and let's have it give us a number. It's 10 million. The number between 1 and 10 million.
Would you need 1 is less than 100 then, instead of 10?
No, because I'm going to do 100 numbers.
Oh, okay.
So I'm going to now say checking to see if num is prime. And then I'll do system.out.println hello.isPrime num. Well, I should make this guy long. Okay. So we're going to do this 100 times. Each time we're going to generate some number between 1 and 10 million. Then we're going to check to see if that number is prime. So we'll spit out saying we're checking to see if some number is prime, and then give us a true or a false. Okay, that finished. If we do 100 million. That didn't go as fast, did it? What about billion? You can see the scales, right? So another time complexity problem with primes. Prime numbers, we can fix this. Instead of going to L minus 1, we can say math dot, I'm teaching you a new function, square root L. Just go to the square root of the number. Already finished. That make sense? So that's a math shortcut for prime numbers. In fact, and even that's not good enough for huge prime numbers. There are websites out there for detecting whether a gigantic number is probably prime. Not even guaranteeing that it's prime. Is it probably prime? So there are approximation algorithms that make a pretty good guess as to whether or not a number is prime or not. Prime numbers are actually a major part of a lot of our modern encryption algorithms for security. How many of you have ever heard of RSA? Maybe even seen it on your cell phone at some point. It's the letters RSA. It's the initials for the guys who founded it, but RSA is an encryption algorithm, and its strength is based on the fact that it's difficult to factor two prime numbers out of one big number. So what you do is, for your private keys, you generate two large numbers that are probably prime. Then you multiply them together, and that's your key. And what they're saying is it's mathematically implausible to quickly get those two numbers back, those two prime numbers back from one giant number. Factoring it is mathematically complex. And that's what the strength of it is on. That kind of makes sense? So prime numbers are another one of these strange forces of nature that don't seem like they're that complex, but the reality is detecting prime numbers becomes a time complexity problem pretty quickly. Okay, so primes, we can do our little shortcut thing here, make it a lot quicker. Let's go back to our fraction code. Let me make sure that we're still slow. Okay, definitely still slow? Okay, so what we're going to do, just to cut to the chase a little bit, here. Euclidean algorithm. Okay, so this is what the algorithm looks like. So we're going to take in two numbers, an A and a B. Go ahead and write this. Static. Actually, let's make ours long because we're dealing with longs here. GCD. This is going to take in a long A and a long B. And this guy says, as long as B is not equal to 0, we're going to keep whittling it down. Okay? So we need to have a temporary variable named T. We'll call it long T. So while B is not equal to 0, what are we going to do? We're going to say T is equal to B. B is equal to, what's it, A mod B? A mod B. And A is equal to T. That make sense? At the very end, we will return A. A is a numerator, B is a denominator. Could be the other way around, doesn't matter. These are two numbers, you're trying to find the greatest common divisor of both of those numbers. That is, the largest number that evenly divides both of them. So we're going to start whittling down our numbers. So until b becomes 0, whether it's the larger or the smaller number, doesn't matter. Until it becomes 0, what are we going to do? We're going to set our temporary variable equal to b to preserve it. Then we're going to whittle b down to something that's a mod b. So we are whittling b down by an amount that's relative to both numbers, our numerator and our denominator. So we're jumping through those, right now we're checking all these numbers in this range. We're jumping through that range by chunks. And the size of that chunk is the number that gives us the possibility of evenly dividing both guys by only jumping by the mod of the two of them. Okay? So we're doing jumps by b, where each time through we're taking a mod b. So we're not just going down by 1. We're not going down by a. We're not going down by b. We're going down by a number relative to both. And in the end, once this is all said and done, a should be our final common divisor. Might be 1. Might be 1. But that path down to 1 should be fairly quick. Let's see this in action. So far, this is our worst case scenario, right? This 13 and 18. GCD 13, 18. Okay, so this is A, this is B. Is 18 a 0? B a 0? No. So right now we have T is nothing. We have A is 13. And we have B is 18. So is 18 a 0? It's not. So since it's not a 0, we need to change some things. So what we're going to do is we're going to set T to 18. We'll set B equal to A mod B. How many times does 13 or 18 go into 13? 0 times, remainder 13. And then A equal to T. Now what just happened there? It automatically flip-flopped the smaller and the larger. So that's why we don't have to check that. It mathematically does it. All right. Next time through, is 13 equal to 0? Nope. So we'll set T equal to 13. B is equal to A mod B. Actually, hold on. A is 13, mod B. Well, hold on, I went backwards though. We need to go back to the previous one. Oh, no, I was just confusing myself because I had pasted our original code.
Oh.
There we go. Now I'll be less confused. Okay, so T will be equal to 13. B is equal to A mod B, so 18 mod 13. 13 goes into 18 one time with remainder 5. There's our 5. And then A will be 13. Okay? Is B equal to 0? Nope. Take all the confusion out. Okay. So T is going to be equal to 5. B is equal to 13 mod 5. 5 goes into 13 twice with remainder 3. And then A is 5. Is B equal to 0? Nope. So T is equal to 3. B is equal to 2. A is equal to 3. B still not 0, right? So T will be equal to 2. B will be equal to 1. A is equal to 2. B still not 0. So T will be equal to 1. How many times does A mod B is 0? 1 goes into 2 2 times with remainder nothing. So that's 0. And then A is 1. Is B equal to 0?
Yes.
Yep. Return 1, which is the greatest common divisor of 13 and 18. That make sense? How that guy works? So it keeps whittling it down, but it whittles it down by strategic chunks.
Do we return T or A?
A. This guy, return A.
They are the same, even the same. Yeah, maybe in some cases the result will change.
What's up?
I mean, in some numbers, maybe the T different than A.
Well, it definitely could be, because
It's
the
always
T could be the previous B. So I don't think you're safe returning T. You need to return A. Because T is always the previous B. So there could be a situation where A and T are differently. All right, so that's what GCD does. So all we need to do now, again, a reminder, notice our code runs slow, right? Still running, still running, still running. Still running. So we need to go and we need to fix our reduce. So here's our reduce. We're doing all of this crap right here. Actually, let's just get rid of all this. We'll call GCD, passing in our numerator and our denominator, getting num. Then we'll say f at bucket 0 is equal to f at bucket 0 divided by num. F at bucket 1 is equal to f at bucket 1 divided by num. That's it for reduce now. Not that the reduce has gotten tons easier, it's because most of the complexity is now in GCD. Okay? So now that exact same function that took forever to run before, you'll see now runs instantly. It's already done. It's done instantly. Ah, finally ran off the end of a long. That make sense? So those are kind of interesting problems. Now let me show you one more interesting factoid. Before I said, what if we want this thing to work for arbitrary size integers? That is, we don't want it to work for, we don't want to be limited by longs. Does that make sense? We want to be able to deal with huge, 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 huge fractions. So I'm going to go to the documentation, java.sun.com. Java SE, Java APIs. I want to say it's in java.util, but let me just find it in this list. Big integer. Oh, it's in java.math. Okay. All right, so here's the big integer class. We can build a big integer by passing it a string. We can build a big integer by passing it a string and a radix, base 2, base 6, whatever. All right, so this is a string representation of a decimal number, not bound by a number of bits. Well, probably is bound by a number of bits at some level. That is the length that a string can possibly be. But, you know, we can have 2 billion characters. Let's say a string, actually it's probably unsigned. So we could probably have 4 billion characters in a string. That's a big number. That make sense? Not the number 4 billion, but the number of digits in the string is 4 billion. That's how big a string can get. I'm just guessing at that. I'm assuming a string length is size of int. It could be size of long. I mean, we see if there's a quick way we can test this. This is kind of an interesting question. Let me comment out this stuff here for a second. I deleted it.
Okay.
Well, let's do it this way. I'm going to purposely write an infinite loop. I think that's 50 A's. Okay. So now, what do we say? For int I is equal to 0. Here goes in 2 million, 20 million, 200 million, 2 billion. Divided by 50, do that. Well, I have 50 characters. I'm just going to I'm going to go through 4 million times and tack on 50 characters real quick, and then start putting out the length of the string. And if we get past 2 billion, then we know we're at least size of normal int. Then I'll jump it to 4 billion. So let's. Did I actually hit it, or the world end? Yeah, we'll race it against Google. How many characters can a Java string have? Okay. Yeah, it's size event. Yep. I need to kill this guy. Where's my there. I think it's stopped now. Isn't it? Pretty sure. Whatever. Okay. So in any case, we have our big integer, and we can build it out of a string. So if I want to have the big integer big integer 10, and it's going to want me to import Java.math. And then I say system.out.println big integer. It should give me my 10. Okay? Now I can say bi.add new big integer 1000, and then print out bi. I should get 1010. That make sense? So big integer allows me to deal with arbitrary size integers, integers of any length. We're not limited by 32 bits or 64 bits or anything like that. Now, having said that, they do get slower the bigger they get. All right, so if you start getting an integer that's out to 150 million characters long, the performance of doing math on that size value is going to degrade quickly. Okay? So what we want to do is we want to upgrade all of our code here to work on big integers. So GCD will take in a big integer and a big integer. It'll store a big integer. While B is not equal to big integer 0. This is a constant inside big integer. Then what are we going to do? We're going to set t equal to b. We'll set b equal to a dot mod b. There's a modulus method built into big integer. This is doing big integer math. So big integers internally know how to do addition and subtraction and multiplication and modulus. So I'm saying a, who is a big integer, mod yourself by b, who is a big integer, returning a new big integer. I'll store that in b. And then ultimately set a equal to t. And in the end, we're not returning a long, we're returning a big integer. That's not really. This is going to allow us to get into the, really see the power of that GCD. Because we'll no longer limit ourselves to a numerator and denominator of 500. Just started off with 2 billion. All right, let's get rid of his prime. It's just hanging out there. We'll keep our random number like this, but we're going to actually have it return a string for us. Actually, we won't. We'll have it return a big integer.
So did none have to be a big integer?
It doesn't, because we'll just assume that they're going to pass us some number in the range of ints to get our big integer, to get our random number started. But in the end, we will return a new big integer created by concatenating our random integer onto the empty string. So we'll return it as a big int, as a big integer. Okay, build fraction is going to take in a big integer num and a big integer denom, and it's going to ultimately return a big integer array. Okay, so that's what that guy does. Reduce takes in a big integer fraction, gets our big integer num, and then calls our big integer and divides it by num. Make sense?
Did one do have to divide by the
Hmm?
didn't one of them have to
Yeah, this is the numerator. This is the denominator.
and we're dividing both of them
No, we're dividing both of them by our greatest common divisor.
by
That num is what was returned by GCD. I see why you're confused. Yeah, it just happened to have a name that was similar. Okay, print fraction is going to take in a big integer. Oop. Array. And it'll print out those two arrays. Or it'll print out the fraction version of those. Add fraction also is going to take in big integers. Say we're adding some fractions. Print fraction already works for big integers. We'll get our common denominator by taking f1 dot multiply f2 at bucket 1. So we'll multiply those two big integers. Then we'll get our new numerator, which is a big integer. So we're going to take f1 at 0 times f2 at 1. And then we'll take f2 at 0 times f1 at 1. And then we're going to say dot add. That guy. Okay. And our answer is going to be a new big integer array. 2 buckets in it. Answer at bucket 0 will be the new numerator. Answer at bucket 1 will be the new common denominator. Then we'll reduce it and return our answer. So now we've converted this whole thing to work on big integers. So we're going to have our big integer array running total. And to build a fraction, we need to pass it 2 big integers. So we're going to say new big integer 1 and new big integer 2. So that's the equivalent of the 1/2 that we had before. Then we'll go through 10 times, adding fractions. Except for random numbers, instead of doing 500, well, first of all, let's just do it with the exact same thing we did before. We'll see it's still fast. Okay, still fast. But now, let's make it work on some big old numbers. Here we go. All right. Pretty clear that we're going beyond the limits of longs and ints and stuff like that, and still was fast, right? Well, we can make this look real cool. Let's do that 1,000 times. Actually, most of the reason this is taking so long is because of the that we're printing out adding fractions over and over again. And let me demonstrate that actually real quick. So where we're doing that is inside of add fraction. These 3 lines. So let me not show those lines. Let's just have it display the final answer. Should take some time initially, but it should happen. Like in a reasonable amount of time, I would think. Where does it say it's running?
If you hover over the run.
Just real quickly, let me switch this to 10 and just make sure our program works. Okay, there's our final answer for 10. I switch it to 100. Final answer for 100. So we could see if there's a delay. If I did it 1,000, we'd get an answer. But thing to understand here, our very first version, look how far I'm scrolling here to get that answer. Yep. So if we had written this program, let's just assume that we can deal with numbers this big. The way we originally were reducing, this program would probably have taken a month to run. Not exaggerating. It may have taken a month of human time. So, time complexity problems are actually fairly interesting because sometimes the easiest problems hide themselves inside of time complexity type things. That make sense? Okay. So what I want to do is we're going to start talking about objects. Your homework assignment, so just as we start doing the next thing we're going to do the second half, your homework assignment is basically do this same thing we did here, but create an object for fractions rather than represent your fractions in arrays. So the problem you're solving for your homework is actually a problem we've already solved. You're just solving it in a more object-oriented way. So what we're going to do the second half is we're going to create another object to solve a different problem. Okay, so it'll be kind of like what you're doing. We're not going to be dealing with fractions. We're actually going to be dealing with parsing a string, parsing JSON code, which we'll talk about. That is another interesting thing for IT people. But the point is that we will be building an object whose job it is to represent a JSON string and to parse it. Your homework, you'll be building an object whose job it is to represent a fraction and to add them. That make sense? Okay, so let's take a 14-minute break. We'll come back at 8, and we'll pick up where we left off. I'll go ahead and get this first video uploading.